Hi everybody, welcome to your first lecture video. So in this video, we are going to cover the slides number 1, which you see here, all the way to slide number 8 of your first chapter's notes. And that should give you all of the information you need for the homework I assigned you for this weekend. I gave you 2 pages of notes, and that's slides 1 through 8 on those pages. So from this one video, you should be able to get them all done and be ready for your next class period at the start of next week. Now, I said in class that every chapter is going to start with a title slide like this, which lists out the sections and some of the content that's in those sections. I mentioned in class that up to this point, as we're going through this chapter, this information here should be like review, and I hope it is because you've seen it before in previous science classes. And this is a good time to start establishing good study habits. Anytime you're given new information in class, whether that's new notes or a new worksheet, take a little bit of time to just try looking over it again or trying the next problem on a worksheet. And I really recommend you start those habits now while the information is still pretty familiar to you, or at least review material before we get into new stuff, okay? And the rest of this chapter may feel like the start of that new stuff. Maybe, maybe not. Now, the next thing you see in each chapter is the objectives page, okay, about the assessments. So the quiz objectives for this chapter have all the vocab, plus the first 18 elements, and some information from a chart that's going to be on slide 12 of the chapter. Now for the elements, you can see here that you need to know the symbol and the name for each one. Just elements 1 through 18 for this chapter. For the symbol, it's capitalization that matters, and we will talk about that in this video, and the spelling of the name also matters. Just like I learned some information about you guys, I really recommend you make Quizlets or flashcards to study that kind of info. We will talk more about test objectives after we get all of the notes done and we start working through worksheets for this chapter. So matter. Matter is anything that has mass and takes up space. And we can categorize it by its state of matter or its composition. And there are 3 states of matter. And I know plasma is a 4th state, but we're just talking about kind of the common ones you would see day to day. And plasma is not all that common day to day. Solids, liquids, and gases. And that's the definition for those right there. If you missed this note in class, anytime you have a word in these videos or in our notes that you have this green highlight on, that's me trying to tell you that this is one of your vocab words, and the definition for it is close at hand. For these, it's directly next to it. Sometimes it's just around it, and you kind of need to read the whole slide as a whole maybe to get the context you need. This diagram is called a phase diagram, and every pure substance, whether that's an element or a compound, can have a phase diagram where we can list out the temperatures and the pressures where that substance would exist at either a solid, a liquid, or a gas. The takeaway you need from this diagram here are these 6 terms that are going to have these green boxes next to them. These are phase change terms, and some of them you already know the meaning of. Melting and freezing, you know what that means, but you can also see its meaning implied with that arrow. Melting is when a change goes from solid to liquid. Freezing is just the reverse of that, liquid to solid. Some less familiar ones are probably sublimation and deposition, but again, you can pick up their meaning here just from the arrow and the chart as a whole. So that's some more vocab stuff for you to learn for your quiz. We can also talk about matter and its categories based on composition, and I'm going to show you those as a flow chart to start off. So matter can be organized as pure substances, and those can be broken down into elements or compounds, or mixtures as the other side of how we can organize matter. Heterogeneous or homogeneous mixtures, and then breaking down homogeneous mixtures even more, alloys and solutions. Now, a pure substance is something that has a fixed composition and a unique set of properties. Elements are the simplest type of pure substance. They cannot be broken down into anything more pure, because once an element is broken, it loses its chemical properties, and so it's no longer a substance by definition. It is just kind of raw matter. Now, we will be able to define that in a couple slides, but an element is the lowest level of matter that still has the chemical properties that make it unique from other portions of matter. There are 118 known elements, of which 91 occur naturally. In chemistry, an element is identified by its symbol. And it always consists of one or two letters, and only the first letter is capitalized. That's a good thing to remember as we start getting into compound formulas and naming substances and looking at their formulas and their formulas. I don't know why I'm searching for a new word there, but the chemical formula of a compound or such, it's only the capital letters. Sorry, it's only the first letter of an element symbol that is capitalized. And for 6th and 7th period, I believe I gave a little example of the importance of that already, and I'll do the same for 2nd and 8th period when I see you again. The element symbol comes from the name, and most of the time, that connection is very clear, like hydrogen is H, helium is He, carbon is C. Sometimes, however, that connection is not so clear. And so for some elements, it's not so clear, and this is because their symbol comes from the more ancient element name. For example, iron has the symbol Fe because it used to be called ferrous. Lead is Pb because it used to be called plumum, and you can see there for potassium, K, kalium. So if you're ever a little confused by the symbol being used for an element, it's probably because that comes from a more ancient known name. Now, let's go a little bit further. Every element on the periodic table has a little box of information there, and that includes not just the symbol or the name, but values that go with it, values that are unique to that element. So in the top right corner of the periodic table in our classroom, that's the atomic number of the element, and it's used to identify one element from the rest. There's also the atomic weight, or the mass of an element, compared to the rest of them. For elements, that term fixed composition that makes them a pure substance means that all of the atoms of an element have the same atomic number, and that's a representation of the number of protons in the nucleus of those atoms. And so something I want you to do real quick is just kind of a simple, fun exercise is maybe look up a periodic table online, and I want you to try to make your name spelled out using element symbols. So think of the capitalization as you use one symbol and then the next, and just try your best. You don't have to get it perfectly, but I would like to see how much of someone's name or of your own name you're able to get down, and kind of see on Monday who was able to get the most of their name done correctly with the element symbols. So anytime you see this little guy in our notes, this little backwards curling arrow, this means I'm asking you to think back at something we've already said, or maybe think back to just a piece of information that I assume is in your prior knowledge, okay? So you notice this line has blanks still, and those blanks are in your notes because we've already stated this definition for a pure substance, and I'm just seeing if you can look back or think back to come up with that definition and fill it in here again. So compounds are the other type of pure substance, and compounds contain more than one element chemically bonded together. This is different than any type of mixture, which is just things in the same physical space, whereas a compound, those different things are bonded together, making something new entirely. For compounds, that term fixed composition means that each unique compound always contains the same elements in the same ratio. And so we've talked about how the capitalization of element symbols is important. Let's go talk about that with compounds a little bit more. So in compounds, the elements and the ratio of elements is important. And if we miswrite that, if we change it just accidentally, then that compound's name must change, and so will its properties. So if we don't get the elements of a compound and the ratio of those elements correct, then we're not talking about we're not talking about the compound we mean, we're talking about something entirely different. So let's look at some examples with just 3 elements: hydrogen, oxygen, and carbon. So if we think about 2 hydrogen atoms and 1 oxygen atom, that's very familiar to you, that's water. In that ratio, we get the liquid that gives life to everything. And so much so that when we, when NASA scientists look out at other planetary bodies and consider, I wonder if that distant planet could support life, they look first for life-giving water that in liquid form. If it has that, then there's potential. And if there's no liquid water, then there's not much potential for life as we know it. Now, if we change that formula a little bit, 2 hydrogen atoms and 2 oxygen atoms, now we're talking about something entirely different, hydrogen peroxide. And if you know anything about hydrogen peroxide, it's used to clean up cuts and scrapes. And it does that by being very good at breaking down cells, and it kind of ends the life of a cell rather quickly. So just a small change in that formula, and now instead of a life-giving liquid, it's kind of a life-ending liquid. And then one carbon atom and two oxygen atoms, switching that out, now we're talking about carbon dioxide, which is a gas that is common in your body, but if you were surrounded by it, too much of it, it could cause you a lot of pain, and it could take away your life. It's not good to just have CO2 all around you. We need oxygen, and we need CO2 to be able to get away from us and mix out, like away from our breathing space. But if you change that even just a little bit down to one oxygen atom, now it's carbon monoxide, and a more dangerous gas now. This is something not common in your body, and it's something that can end your life even quicker. One carbon atom and three hydrogen atoms, now we're talking about a different type of gas. We're talking about something that's explosive. We're talking about something that's flammable. And so I hope you can see that just a little change in the element or the ratio of elements can mean drastic changes in the actual compound we are discussing that is being referred to. And so I'd like you to just let this sink in. Even small changes in chemistry can have big effects. And we're going to talk more about this a bit on Monday, because when we're in lab together and we're doing experiments and we're following a procedure, if someone goes off script and changes that procedure, does something that's not instructed, and they make even a small change, we could get big effects, and those may not be beneficial. The surprise would probably not be worth the results of it. So let's talk a little bit about this idea. The properties of a compound are usually very different from the properties of the elements within it. So we have three substances here pictured. We have an actual picture down below, and then we have a little atomic model in a bubble above it. So here we have something that looks like it's in its solid state. It's kind of gray, kind of shiny, and it looks like someone has a glove on that's holding it, and they're pushing a knife blade through it to bring chunks of it off. And then we have this model of it, of these like gray spheres all stacked together in a very rigid kind of repeated pattern. Then we have a vial or a flask of some kind of foggy substance. Notice how it's taking up the entire container. So that would be a gas. It's a little bit, we can see through it. We can also see in this model that the different particles of it are not all touching. It looks like it has pairs of particles, but then those have space between them. Another evidence that we're looking at a gas, not a liquid. And then over here, we have a crystal structure, something clear, almost looks like a grain of like sugar or salt or something. And you can see in its model, it showed it as a mixture of these two colored circles, but now they are connected, all one after another, not just mixed, but connected completely or bonded together. And so this is an example of a compound. So let's talk about what this actually is. So we have sodium, which is a metallic element that is soft enough to be cut with a knife, which is kind of interesting for metals. We don't often think about metals as being soft, but some metals are, not just in their pure form, but they are in general, soft enough to be cut with a knife, sodium. Okay, and then you have chlorine, which is a non-metallic element that's a gas. So we have one metal and we have one non-metal. We have one solid and we have one gas. And if you know anything chemically about these elements, you might know that sodium reacts very violently with water, which is why whoever's holding this has a glove on, because they don't want any moisture from their hand to interact with that sodium metal. And then if you know anything about chlorine gas, you know that it also has kind of harmful effects. I shouldn't even say kind of. It's very poisonous. This is not a gas that you want to breathe in. In fact, it has some infamous uses throughout history as a way of taking life in large scales. But I'd like you to imagine what would happen if you put this little sliver of the sodium into your mouth. Well, we already said it reacts violently with water, and your mouth is pretty much full of a lot of water, And so if you did that, you would have a violent reaction in your mouth that would cause a lot of damage. And then we just talked about how this gas is poisonous. It is not good for you. And so when you put these two things together, one is harmful with water or violently reacts with water and would be very harmful if you were to try to ingest it. The other is a poisonous gas and would definitely hurt you if you had exposure to some of it. But when you put them together, we create what's called sodium chloride. And if you're not familiar with that, that is the name of table salt. It's a crystalline compound formed when sodium combines with chlorine. And it makes these little crystals that we pour on top of our French fries and our potato chips. And I want you to just take a second and understand how bizarre it is that in the pure form, sodium is an explosive metal. It's a metal that is explosive and reacts violently with water. And then chlorine is a gas that is poisonous. And yet together, they make a compound that we not only enjoy eating, but we actually need it in our diet. We need it to help our body function the way it's supposed to function. And so this is just an illustration of that line you wrote down. The properties of compounds are usually very different from the properties of the elements within them. And so again, we're going to emphasize the importance of detail of naming something and knowing its formula correctly, because the formula it identifies the correct substance, and that substance has unique properties that we have to consider, even from the elements that make up a compound. So now we've talked about pure substances, elements, and compounds. We're going to talk about mixtures now. So mixtures contain two or more substances combined in such a way that each substance retains its chemical identity. Let's contrast that real quick to the compounds here. So we had a metal that was violently reactive with water. We had a gas that was poisonous, but when they combine, they make a crystal that can be mixed with water without a violent reaction and is not poisonous. And so the properties of these things, when put together, combine to make something new. The crystal of salt is a new thing based on the bonding of sodium and chlorine. However, with mixtures, things can be combined but not bonded. Each thing retains its chemical identity. It is just mixed in with other stuff. And there are two types of mixtures. We're going to look at this chart here, but this is going to finish off your notes. So a heterogeneous mixture means the particles are distributed non-uniformly, or not evenly mixed. So you can see in this diagram, you have all these dark blue circles up top, light blue circles on the bottom, but look, one dark blue amongst the light blue. It's not evenly combined. Like cereal and milk, the cereal usually floats to the top, and so you have much more cereal at the top of the mixture, much less cereal at the bottom of the mixture. Same with ice and soda. It's not evenly mixed. The ice is concentrated at the top, whereas it's not as much at the bottom. Soil, of course, or dirt, or anything kind of a natural rocky substance is a heterogeneous mixture of many, many things. But then heterogeneous mixtures can be a little bit tricky sometimes. Even blood, which can look pretty uniform, is actually made up of different pieces that aren't evenly blended. And we can talk about that a little bit more in detail in person. Whereas homogeneous mixtures, if we look at this diagram, the light blue and dark blue circles are evenly spaced throughout. Particles are evenly distributed or uniformly distributed. Okay, like an alcoholic solution, whether that's drinking alcohol or rubbing alcohol, it is evenly mixed throughout. Steel, which is a combination of iron and carbon, is evenly mixed throughout. The air around you is an even mix, and one of the ways we can understand that is pretty much everywhere on the planet we can breathe normally above water above water, at least in the open air. It's all kind of the same. Now there might be some places of higher pollution than others, but when you think about the globe as a whole, the air is pretty well evenly mixed. There's not like patches where people can't breathe. Now you might be thinking, what about high elevation? Well, think about that, and we can discuss that when we get back to class. And rain is an even mixture as well. Again, there might be some examples where that gets a little uneven, but let's just think about that. And if you have any questions, bring that in class. Let's talk it through. But now this ends your video. This gets you through your content for the weekend, slides 1 through 8 of chapter 1.